lab 5. So, introduction, what we did. The purpose of this lab is to predict the motion of a falling slinky and analyze the effects of these surroundings. We use Tracker to observe the position and compare that data to a computational model created in GlowScript. And basically, the goal was to prove that the bottom of the slinky stays stationary and model what that movement looks like in GlowScript. We found that the gravity plus drag computational model was very close slash similar to the observed data, proving that the bottom of the slinky remains stationary, and we'll look at that in just a moment. So, just real quick, this was the tracker data. The system was slinky, the surroundings was the Earth, and these were the initial conditions. So, I estimated the mass of the slinky to be like almost 2 kilograms. I put it as 1.72. This was the starting height, 5'10", just because, I'm assuming that the guy in the video is around 5'10", and you can see the calibration stick right there. This is the initial position from the tracker data, and this is the initial velocity, which because, the slinky's starting at rest. Um, and just real quick, before we get into the models, there is a little bit of discrepancy. The models are very close, but or the model is very close to the observed data, but the discrepancy could, maybe be due to, um, in real life there's like we don't know the drag constant. There's some human error. It isn't super recreatable, and there's issue with the tracker video. Whereas the GlowScript model is like a, perfect case scenario with, you know, um, you can change the error resistance however you want. The data is always consistent, et cetera, et cetera. So that's where that slight discrepancy comes from. As for the fundamental principles, it was Newton's second law. We've used this in almost every lab. You basically need this to, create the model to show the movements, to update the movement. There's the drag force, and then there's the force of the slinky that opposes the force of gravity that keeps the bottom of the slinky in the air. Um, so how we created the model, this is just some code. On the left, you have the initial conditions that I described earlier. So the initial mass, the ball's position, et cetera, et cetera, et cetera. And this is the actual calculations loop. So this is where Newton's second law comes in. Um, we calculate the force of gravity, the force of drag, we use that as the net force, and we use that net force to apply the momentum principle to update the velocity and the position. Here were some of the results. So the green line is the bottom of the slinky, and the orange line is the top of the slinky. And you'll see that you know, and this is the observed data, by the way, but you'll see that the bottom of the slinky does stay pretty much the same. There's like very slight variation, and again, that's due probably to tracker discrepancy. But yeah, you can see the bottom of the slinky stays pretty much the same, and the top of the slinky slowly falls. And around this point right here, where the lines intersect, is where um, the top of the slinky hits the bottom of the slinky, and they start falling together at the same time. And over here is the tracker model, which is in orange, and the actual model, which is in purple. Or sorry, the tracker data, which is in orange, and the GlowScript model, which is in purple. And you'll see that they are very close to each other. Um, very, very slight discrepancy, but yeah, the model shows pretty much, uh, what we observed. So what do these results mean? The bottom of the slinky did in fact stay stationary. This happens because the slinky is still under tension. So the information that it has been released takes time to travel downwards, right? Once the change reaches the bottom, the entire slinky falls. The model and the tracking data are very close. So we estimated a pretty solid drag constant. And this supports the main conclusion of the lab. The bottom of the falling slinky remains approximately stationary, right? That was our goal that we defined at the beginning. And some what ifs, what if there was no air resistance? The model would look different. Um, what if the slinky had a larger mass? The timing and the shape of the fall would change, right? If you had a very heavy slinky, the top would fall quicker, and that would impact how the model looked. What if the slinky were stretched before the release? The delay before the bottom, it would take longer for this for the slinky to fall, right? And so the bottom would stay stationary for longer, And if the tracker data were more precise, if it were like spot on, we'd be able to estimate a perfect exact drag constant. Because at that point, we just have to have a model that fits one to one. But since the data has variation, the model is going to have variation as well. That's it for the lab. Thank you all so much.